Today's lecture is going to be an exciting one because we're going to learn an entirely new law of physics that's actually very handy for calculating electric fields. In fact, you will see that it is much more convenient than the very grungy and detailed types of calculations we've had to do in the past, where you have to integrate up contributions from all of the charges constructing a system. Now, in order to get to that point where we'll be able to do this, I need to emphasize several key results from the last lecture that we will be drawing upon. The first of these is the principle of superposition, which simply tells us that if we have some complex situation or arrangement of charges, and we want to obtain the electric field for that complex situation, we can actually decompose it into the individual components comprising the charge density, maybe a plane of charge or a line of charge, and then simply add up the electric field results that we already have in our database for those particular planar or linear charge distributions. Now, in order then to understand how we can use this new physical law to compute the results for these various contributions to some overall complex charge distribution, we were reviewing certain key aspects of the flow of fluids. We had done two things, really. We had reviewed in general the physics of flow, sometimes known as flux. That's simply the Latin word for flow. We were discussing that in general. And then we had this very particular application to what we had called a fluid model that's going to allow us to intuitively understand this new physical law for electric fields. So let's review these here one at a time. When we begin to think about the physics of flow, there were a series of definitions and then some key mathematical results. The first definition is the density of the quantity that's flowing. And by the way, generally these results are most useful when you are dealing with a quantity that is conserved, something like mass in the case of fluid flow or charge in the case of flow through a circuit. Now, the density then is defined as the conserved quantity, either mass, but then per unit volume for the fluid, or charge per unit volume in the case of current flowing through circuits. The current, there's the current, which is the amount of our quantity passing through a given surface through a given amount of time. And that's measured then either as mass per time in the fluid case or charge per time, as you've already seen a little bit of in some of the practice exercises when we are talking about current in a circuit. As we go further, we then came across a new concept, the current density, which is a vector, J vector. The magnitude of the vector is defined as the current, whichever kind you are measuring, per unit area, because it's a density per area. The direction of the vector, which we also have to define, is simply defined as equal to the direction of the flow of the underlying conserved quantity. Now, we can put all of these various definitions together as we began to consider a physical situation where we had some fluid of density rho naught, which was flowing with some velocity v, and we considered then what happens, how much of that material or quantity is flowing through a particular little tiny patch of area, measured by a vector, delta A vector. The magnitude of that vector tells me the area of that patch, and the normal to that area gives me the direction of the delta A vector. Now, with that specification, what we found were the following intriguing results. The first was that the current density is easily obtained in terms of the volume density, namely the volume density times the local velocity of flow of the quantity V. That then gives us the current density directly. With that current density, we then can determine actually the total amount per unit time of the quantity flowing across the surface, namely the current, and it's simply the current density, J, which is current per unit area, dotted with the area vector. We can see that current per area times area should give us current. This dot product is taking care of an important physical aspect, which has to do with the following. We know, for example, or we can see that if the velocity is straight towards the area, right, I'm going to get quite a lot of flow going through it, as opposed to if the directions are a little bit different. If the velocity is actually parallel to the surface, coming this way, there will actually be no flow through the surface. and this dot product takes care of all of that automatically. We had done a very general analysis in the previous lecture to make sure that that was accounted for properly, but you can see that if the flow, J, for instance, is perpendicular to the surface normal, that dot product will give me the cosine of 90 degrees, and the cosine of 90 is 0, and there being then no flow, the cosine will give me 0, and I will find 0 current across the surface, as I should obtain. Finally, we noted that if we want the flow across not a tiny little patch, but some actual maybe complex surface, we simply have to add up, in other words, integrate the flow across each of the tiny little patches dA, which comprise the overall surface. We then integrate J dot dA across that surface. The final key thing to keep in mind about these types of integrals is that always, once we are in a situation of steady flow, if we are dealing with a conserved quantity, right, which then we know by conservation of either the mass or the charge or whatever the quantity is, that in a steady flow case, the current flowing into a region has to match the current flowing out of the region. Otherwise, we'd be building up quantity in our region, and that would not represent a steady flow. Something would be changing. The second thing we did was we then built upon all of this physics of flow to construct a model, a mechanical model of the electric field from a point charge. And what makes this very exciting is that if this model works for a point charge, because we know the specific kinds of flows we are studying actually obey the principle of superposition, and we know that any electric field can be constructed by superposition from tiny little point charges, this fluid model then will work for any type of charge distribution. We can simply put in our fluid model for point charges, arrange them the same way for whatever electric system we're trying to understand, and then we can simply measure the velocity in the fluid, and that will tell us exactly the value of the electric field, provided we're able to show that the flow field from this fluid model for a point source matches the electric field for a point charge. So we were going about trying to carry out this calculation, and here's what we found. We applied our conservation of mass, in this case, that the total current flowing into this spherical region of radius r has to match the total current flowing out. Now, the current flowing in is actually set by our faucet. That's the hose that's pumping a current. A certain amount of mass per unit time goes down this hose. It then comes out of the little sprinkler ball, equally outwards in all directions. And then finally, it leaves this spherical surface at the surface. So we can equate then that incoming current I to the outflow, and to compute the outflow on this sphere, we have to take the flow out of every little surface patch and add them up across the surface. In this case, we are using a closed surface, so we know we are accounting for all of the flow, so we use the double integral sign with a loop indicating the closed surface. We then went about evaluating this integral. First, we expanded out the dot product, which gave us rho times the magnitude of the velocity, times the magnitude of the area vector, which we can just call dA, times the cosine of the angle between them. In this case, the velocity is outward from the center, and that's in the same direction as dA. So that gives me the cosine of 0, which is 1. We then noted that the density and also the velocity, its magnitude at least, should be constant across the surface by symmetry. All these points are equal distant from our source. So we could pull rho naught and velocity out of the integral. That just left us with the area 4 pi r squared times rho naught times the magnitude of our velocity. Then finally we solved for the magnitude of our velocity was the incoming current pumped down the hose divided by 4 pi rho naught and also r squared, and the direction then was directly outward. And my final observation in the previous lecture was that I was very excited about this result because I've got the same 1 over r squared type of behavior that we normally see for a point charge. We're going to see, though, that the analogy goes much, much deeper than that.